Welcome back to our series on organic reaction mechanisms. In this video, we are diving into a fundamental transformation in organic chemistry, electrophilic aromatic substitution, commonly known as EAS. While benzene is exceptionally stable due to its aromaticity, it can be coaxed into reacting with high-energy species called electrophiles. In this video, we will break down the universal mechanism that governs how these reactions unfold. In an EAS reaction, benzene acts as a nucleophile, reacting with an electrophile, E+. Unlike alkenes, which undergo addition reactions, benzene undergoes substitution. This is because substitution allows the molecule to regain its highly stable aromatic system. The overall transformation involves the replacement of a hydrogen atom on the benzene ring with the electrophilic group E, yielding a substituted benzene ring and a conjugate acid HB as the final products. Let's examine the step-by-step electronic dance that makes this possible, using benzene and a generic electrophilic reagent, EB. Step 1. Formation of the sigma complex, Arenium ion. The reaction begins as the electron-rich pi system of the benzene ring attacks the strong electrophile, E+. As two pi electrons move to form a new carbon electrophile sigma bond, the aromaticity of the ring is temporarily broken. This first step is the rate-determining step. Breaking the aromatic resonance energy creates a high-energy intermediate called an Arenium ion, or a sigma complex. Although the ring is no longer aromatic, this carbocation is somewhat stabilized by resonance, as the positive charge is delocalized over the ortho and para positions. Step 2. Deprotonation and re-aromatization. To restore its lost stability, the Arenium ion must lose a proton. A weak base, often the counter-ion of the electrophile, approaches the ring and abstracts the proton from the sp3 hybridized carbon bearing the electrophile. As the CH sigma bond breaks, the two electrons from that bond collapse back into the ring system. This instantly restores the full 6-pi electron aromatic circuit. Now, let's take a closer look at the Arenium resonance hybrid to understand what's really happening during this transformation. As the benzene ring attacks the electrophile, it transitions into a high-energy intermediate, known as the sigma complex, or the Arenium ion. At this stage, the exceptionally stable aromatic sextet is temporarily broken. However, the system doesn't simply collapse. It remains partially stabilized through resonance delocalization. It's important to remember that the true structure of this intermediate is best represented as a resonance hybrid. Instead of a fixed positive charge sitting on a single carbon, that +1 charge is actually primarily distributed across the ortho and para positions, relative to the newly formed sp3 hybridized carbon. Take a look at this 3D model. You can clearly see the horseshoe pi system, where electron density is spread across 5 p orbitals. Notice how the partial positive charges are strategically concentrated at the specific carbons where the delocalized electrons are most efficient. This unique horseshoe representation is vital because it highlights that the sp3 carbon, the site of electrophilic attack, is completely excluded from the pi system. This creates a distinct gap in the electron cloud, which ultimately defines both the reactivity and the high-energy nature of the Arenium ion. Let's summarize. Step 1. Nucleophilic attack. Benzene attacks the electrophile. forming a resonance-stabilized Arenium ion. This step breaks the aromaticity and is the slowest part of the reaction. Step 2. Deprotonation. A base removes a proton, allowing the pi system to close and restore aromaticity. Let's organize by keywords. The initial attack on the electrophile is the RDS, as it requires a high activation energy to overcome and break the benzene ring's stable aromatic resonance. This high-energy, non-aromatic intermediate is stabilized by resonance, with the positive charge delocalized over the ortho and para positions of the horseshoe pi system. The restoration of the aromatic sextet provides a massive stabilizing force, making substitution energetically favorable over addition. Those who wish to deepen their understanding of EAS are encouraged to study the following topics. If this video was helpful, we'd really appreciate it if you could share it with others. See you in the next reaction.